L by 4. Thermal conductivity of this yellow color rod is K. 2K. Length is 3L. Area of cross section, let me make it same. It'll be easy for us. This L by 2. Thermal conductivity is K. Length 3L. Okay. K by 2, I'll write it. Now I want the effective resistance across X and Y. Look at this rod. I'm just wanted to find out. So what is this length will become? 3L by 4. This is L by 4. Here at midpoint, I'm connecting it. So shall we, so if I send any, if I maintain temperature difference, the heat will branch here, no? And what all that heat flow, the same heat will flow across. Even area of cross section, you can make it different. Huh? So timing, let me assume same area. So it'll be easy for you. If you want, okay, one rod, I'll make it 2A. So that 3A let it be, yeah. Okay, they are made a connections. Let's not bother how they're connected. Let's not bother. Okay, this is 2A, no? Let me make a little bit thick. How that connections are achieved, let's not bother about that. Huh? Okay, now get into the problem. We have to calculate effective resistance. So here I'll do one thing. This length 3L by 4. So this will have one resistance. So equivalent circuit diagram, I'll plot it here. This is the one thing. Then the lower part. This is Y, this is X, no? So call this is R1, R2, R3, R4, R5, R6. Symbols will take analog. It'll be easy. R3, R4. Let this be R5. Let this be R6. What is R1, R2? We don't know. How to calculate R1? R1 is equal to length 3L by 4 by thermal conductivity K, area of cross section A. And how R1, R5, R3 are? They are in series, no? We'll agree this. So what all heat current that comes will branch here. So and this same current will pass through across all these three elements, R1, R5, R3. So here the heat will branch. So therefore, this effective resistance will be in parallel with this one. And these three R1, R5, R3 are in series. So therefore, I should add up. So let me go for the upper part, R153. Let me calculate. So this will be R1, R5, R3. And what is the value of R1? 3L by 4 by K. What is R5? Length is 3L. Thermal conductivity 2K and area of cross section 2A. Next, what we get? L by 2, K by 2, A. So this will become 3L by 4K, 3L by 4K, L by K. 3, so this will be
5 by 2, sir.
total, huh? Yeah. Okay, this is R153. Similarly, R265. Okay, this R2 will be L by 4, L by 4 KA, R6, 3L by 2K, 3A, R5, L by 2, K by 2, A. This will be L by 4K, L by 2K, L by KE.
1.
This will be 1, huh?
Yes. L by K.
How come 1? It will be 3 by 4 plus 1, 7 by 4.
Sir, last term is L by 4K.
Oh, this is... No, how will be? 1 by 2, 1 by 2 will cancel, no?
Sir, it will be 7 by 4, sir.
7 by 4. I know a little bit maths, huh? Okay, now how these two are? How this, they're parallel. So the effective resistance Rxy should be equal to, again, they're parallel. So this will be better idea. Let me go for it. Huh? So that to minimize calculation. So R135 plus. So this will be 2Ka by 5L, 4Ka by 7L. Two by 5 plus 4 by 7. Anybody value Rxy?
35 by 34.
35 by... So this will be the effective resistance across
by
this
34, sir.
34 by 35.
34 by 35, huh?
Sir, 35 by 34.
35 by 34. Okay, no. Look at now. So this is the effective resistance. So now if I give temperature difference, can we calculate how much of heat current will flow here? Okay, you have to go back that parallel we discussed, no? The parallel one. These formulas will help you. If I know what is the heat current, what is the heat current is entering here, how much of heat current in individual branches, these formulas will help us. So suppose here if I say that 10 joules per second is entering at X, then how much of thermal power will pass through this one? So what we should use this particular formulas here. If H is heat current here, so let me give like this. How much in upper part, then how much in lower part. So can we calculate this HU? So what is H? 10 joules per second. So how much will heat will pass through this upper section? How much will pass through the lower section? So any formula, again, I'll go back to this one. HU is equal to H into resistance of lower part. So that will be R265 by total resistance R153 plus R265. Similarly, how much of thermal power or heat current is flowing through the lower part means the total heat current that is entering the junction X by resistance of upper part R153 by. These are the types of questions what. So here we are discussing like some current density, but in exams what happen, you get like this. They say like a 10 joules per second is entering here. Then how much of heat current will pass through here? So don't say phi and phi. It depends upon this ratio. Then what is the temperature difference across this? So can we calculate temperature difference across the brown color rod? How to calculate this temperature difference? I think if you know how much of thermal power here, how much of heat current, we can calculate the temperature difference. So now I want temperature difference delta T phi. How to calculate delta T phi? So next set of problems will be delta T phi will be HU into the resistance R phi. Now I can go for temperature difference across individual elements. These are the types of this is what it is going to help us. If I know the heat current here, I can calculate the temperature difference. So now what is the type of questions what you get is like, find the temperature difference across this rod. somehow if you can calculate the temperature difference, okay, this will be shared by these three, no? What all the temperature difference here will be shared by these two. You can go for series side here, or any of this method. So I'll write it here. Delta T5 is equal to, similarly, what is the temperature difference across this rod R6? So delta T6, you can write it as HL by R6. Like this, what happened? We can determine the temperature difference across individual elements also from this. I think like these are the types of questions which are just based on the Ohm's law, series parallel. Those ideas, if you apply, no, you'll be in better position. Okay, once again, we are discussing all the numericals where at steady state. It's quite clear now. We are discussing all the numericals open at steady state only, or properly lagged. The rod is properly lagged. What will be the state of the rods here? None of the part of the rod will be involved in absorption of heat. What all these segments of the rod will do, of different segments of any rod, they'll be only involved in transfer of it.